Good evening and welcome you all for this webcast. This is Anupriya representing IChrom. Hope you all are safe and well. Today's webinar is based on NMR Characterization, which is going to be represented by our mentor Dr. Mohit Kapoor, who is an assistant professor at Chitkara University. He did his studies from Taiwan and USA. His major focus was on sustainable organic and medicinal chemistry. Currently, he is working on MRI agents and antiviral therapies. Now, welcome Dr. Mohit. Please, Dr. Mohit, go ahead.
Sure. I need my screen. All right. I think everybody is able to see my screen.
Yeah, Dr. Mohit.
Okay, great. Thank you. All right, guys. Good evening to everyone. And so, as Ms. Anupriya already introduced me, that basically my research work and my studies is related to organic chemistry, and organic chemists always go behind the NMR, because without NMR, organic chemist, or these days in any field of chemistry, NMR is pretty important. Without NMR, you can't move forward. So today we'll see some basic things and how to interpret quickly the NMR spectrums, because once you undergo with the research, and you have several reactions or several molecules to identify, that time the tools and techniques which helps to get quickly the structure is important. So yes, and so the thing is that that's what is my concern here, that we will see how to identify the structure quickly. So that's the reason I put the topic, the title of the topic is the practical aspect of NMR interface and characterization, and is certainly the panic when it comes through the for the thesis. I'm hoping that most of the audience here have the knowledge about NMR, the basic knowledge about NMR, and we will, of course, I will touch the base of NMR with the time, and let's see how it goes. So, all right, let's move forward. So, as you know, everybody knows that NMR spectroscopy is nothing but the structure identification tool in the field of chemistry and biology, right? So as you can see from the title or from the name, the nuclear magnetic resonance. What that means, that nuclear magnetic resonance means the nucleus of any atom. The nucleus of an atom is under the resonance with the magnetic field. So thing is that the nucleus have the electrons. Once you apply the magnetic field, the electrons align in direction, they rotate. As you can see in the figure, they rotate and they have their own magnetic field. You know the flux. Everybody know the flux, right? Once the electron rotate, the nucleus rotate in align in the magnetic field, they have their own magnetic field as well. So so the thing is that now what kind of atoms. What kind of atoms? All the atoms will behave or will show up in the NMR. All the atoms will have the magnetic resonance. Which atom have the magnetic resonance? To make it very simple, we outline the table here. So you see this table is pretty easy to follow, is easy to understand. We don't have to have the so many equations to derive that, oh, which molecule or which atom will give us the resonance signal. So if you see the table here on this slide, you can see that if the atomic mass and the atomic number both are odd, means you can see the example of the nuclei is a proton 1H or tritium 3H, the hydrogen isotope with 15.7, fluorine isotope with 19.9, and phosphorus isotope with 31.15. So all of those are having half integer. Now the one, what does that mean? In the parenthesis of the nuclei, you can see half, right? What that half means is a spin nuclear number. So the thing is that the spin nuclear number should be odd, half, right? It should be half, or 3. But the thing is that if it is 0, as you can see in the last row, if the I is 0, means atomic mass and atomic number both are 0, means that nucleus, that atom is not active in nuclear magnetic resonance. You cannot see that molecule, right? Even though it's 1, you cannot see that. So it should be in the point integer, half 1 point, 0.5. So the example of the nuclei means, what to say from this table is that is easy to follow that which molecule will give which atom will give you the NMR signal. Now what is NMR signal? Why I'm saying NMR signal? NMR signal means which nucleus will be in the resonance with magnetic field. That's easy to follow, right? Which nucleus will be in the resonance with the magnetic field. So the half integer nucleus will be in the resonant field. So once we apply the magnetic field on these nucleus, you can see some peaks. You can see some peaks in the NMR, right? So so basically from this slide, what we can understand is that not all the atoms have the NMR signals. Only the atom where the electron is of half spin is unpaired can undergo NMR, right? So before we move forward towards the advanced techniques for the NMR, I would like to draw your attention to the instrumentation. So basically, there are two kind of instruments people used to use in NMR. One is a continuous wave CW, and these days is FTIR, is a Fourier transform. So currently, everywhere is FT NMR, not CW NMR, right? Mostly we use FT NMR because the application has been increased. So we need a high frequency to do all the characterizations and to use the NMR in all the applications. Not only in organic molecule, NMR is useful in the biologically active molecule as well as in DNA, RNA, proteins, etc. If anybody have any concern or question, I will take in between. So write down your questions in between. So we will see the question at 6 once before in the break. Okay. So the instrumentation. So this is the instrumentation for FT-NMR, the Fourier transform. So FT-NMR is, as you can see, that the long rod is the magnetic board where you insert your sample. So inserting the sample here means you insert the sample in a tube. You see, this is itself is a tube, right? This is itself is a tube. You insert the sample in a glass tube. You have the sample in a special NMR glass tube. That special NMR glass tube is of particular width and diameter. Is of particular width and diameter. So that NMR tube, that glass tube you use for the NMR. So you dissolve the sample in a liquid, in a solvent. I will discuss with you that in the some later slide. So you dissolve the sample in some liquid, some solvent, take in that NMR tube and insert the tube in this magnet bore. Now, how to, as I just mentioned, your sample will be under strong magnetic field. How to generate strong magnetic field? The strong magnetic field will be generated with the help of the magnetic coils. Now, magnetic coils is, of course, if as we increase the frequency of NMR, as we go from 60 megahertz to 90 or 100 megahertz to 300 megahertz to 400 megahertz to 600 megahertz, and these days up to 900 megahertz. If you want to create that strong magnetic field, if you want to achieve up to that frequency of 900 megahertz, you have to have something to cool down, because the magnets get heat up very easily. So you see the magnetic coils are here. The surrounding of the magnetic coils is the liquid nitrogen as well as helium. So these two liquids is here just to cool down the cool down the temperature of the magnets, right? So the instrumentation consists of a magnetic bore having the magnetic coil as well as the shimming coils. I will explain what is the shimming coils. You have the liquid nitrogen as well as the liquid helium. The how to purge it or how to fill it is from the side. These days in every university, people have the students have the turn to fill up the liquid nitrogen and the liquid helium. The universities or the institutes where the NMR is available, there the students take the responsibility to fill up the liquid nitrogen and the helium in the instruments. All right, so you have the magnetic bore, you put the sample inside the magnetic bore, fine, you have the probe under that. Now what happened? Your sample will come under the influence of this magnetic coils and the shimming coils. Why? Once you start the process of NMR, intense magnetic field generated, which rotate your sample at very high speed, and until it aligns with the magnetic field, the shimming coils will help to get the alignment. Now, this can be controlled manually. You can control how you are shimming your sample. What that means of shimming? The, the shimming of the sample means you are placing your sample in a proper magnetic field, in a right magnetic field. You're placing your sample in the right magnetic field, or on, I should say in other words, you are aligning your sample nucleus along with the magnetic field by using shimming coils. So this can be done manually. This can be done manually or automatically. The Bruker, if the person, if you guys are aware of NMR, you know the Bruker and the Varian, right? Most of the time, Bruker NMR can do the automatic shimming. The Varian NMRs, we have to use the manual shimming. So, all right. Anyways, even though you can do the automatic shimming, you can always switch the shim from automatic to manual anytime. Anyways, the thing is that once you do the shimming and place your sample in proper magnetic field, that's the time, that's the thing that everything starts. Once you place in the magnetic field, once you place properly in the magnetic field, that's all. You have the receiver and the quadric and the detector. Now, as everybody knows, as we know, the concentration of the nucleus is less in the sample. What that means is less. What that means, why I say the concentration of the nucleus is less. Thing is that here we are not, here we are dealing with the isotopes. Some of the isotope of the atoms are in the less abundance in the nature. For an example, the carbon 13. The carbon 13 nucleus is already in very, very minute quantity in molecule in a carbon species. So if the isotope is present in less amount, you need some amplifier to amplify the signals, because as I just mentioned in on my first slide, not all the isotopes is active in NMR. Only few are active in NMR. So few of those are which one? As you can see from the my table second row, 13C6. Why? 13C6 is an isotope. 14C6, 12C6, all these are isotopes, but 12C6 is in abundance, but 12C6 is of no use because the integer or the spin quantum number or the spin integer is 0. That is not active, as you can see in the last row, right? As you can see in the last row, 12C6 having 0 value, this is not active in an NMR. So half integer means 13C6 is only active in NMR. But if we are dealing with 13C6, the abundance of 13C6 is very less. So that's the reason you need an amplifier. That's the reason you need an amplifier. Now that amplifier will amplify the signals. Sometimes you have the noise because you have some impurities in your sample. You need some filters, some converter, and reach up to the computer top, and that gives you the output signal, right? So in short, you have your sample in the magnetic bore along with the liquid nitrogen and the liquid helium in the surroundings. When you start the magnetic field, temperature get higher inside the inside the NMR machine, because so that's why we have liquid nitrogen as well as the liquid helium to cool down the temperature, and then is the shimming coil to place a sample properly in the magnetic field. There's a shimming coil work to do that, and then once you have the shimming properly, that time you start to receive the signals. You start to receive the signals, and then you have the amplifier and filter. All right. So basically, you know, sir, the 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 layout, how is the instrument works, right? So as I just mentioned, you have to dissolve your compound in some solvent. So see, I'm not covering here enema, the very basic or fundamentals of enema, those that anyways cannot be covered in 3 hour or 2 hour, right? So I'm covering here all those things which you need to know once you are on the bench in your lab and you have to do the enema, right? All right. So solvent, what kind of solvent? Right. Now, see one thing. Nuclear magnetic resonance, NMR. Basically, we do NMR for the proton, for the carbon, right? But every molecule have hydrogen, carbon. So how to do NMR if every molecule means everything will show up in the NMR? No, no. Not everything will show up in the NMR, but every molecule, every atom, every DNA, RNA, all the organic molecules have carbon as well as hydrogen. So you cannot use any of those as a solvent. You cannot use any of those as a solvent for your sample to dissolve in NMR. So remember, to tell, I thought to, I should tell one thing, that we have to dissolve our sample in some solvent. Now, what solvent? That solvent should not have proton. That solvent should not have proton. That solvent should not react with your compound. That solvent should not be expensive. It should be inexpensive. Of course, that solvent should be volatile. Means once you done with the NMR, you should be able to recover your sample, because sometimes the sample is very precious. Huh? Sometimes the sample is very precious, right? So you have to have the volatile solvent for NMR, right? Now you know that the basic thing, it should not have proton, it should be inert, should not react with your compound, it should be inexpensive and volatile. Now what is the solution? Deuterated solvents. Now what is deuterated solvent? Deuterated solvent, the solvent where the proton is exchanged with the deuterium. Deuterium is the another isotope of hydrogen. Deuterium is not active in NMR. So we have to use those solvent which is not active in NMR. Means deuterium, deuterated solvents. Any solvent where the hydrogen is replaced with deuterium can be used for the NMR solvent. Now remember one thing, as I said, it should be inert and inexpensive. So the most common solvent we use in NMR is CdCl3. CdCl3, or is CD3OD is methanol. So what is CdCl3? Is CHCl3 is chloroform, but the deuterated form of it is CdCl3. DMSO D6, dimethyl sulfoxide. So CH3SOCH3, there you have 6 hydrogen. Those 6 hydrogen is replaced with deuterium. Similarly in acetone, similarly in methanol. So all those solvents, if you replace the hydrogen with deuterium, you can use them as a solvent for NMR, so that it should not interfere with our compound, our molecule NMR. Now, how it work in the NMR? I, of course, all this CdCl3, DMSO, acetone, CD3OD now having the deuterium, but all those samples, all those solvents have some impurities, have some impurities. Now what is the impurity? What could be the impurity in these solvents? So the very simple thing to know that the impurity could be the starting material. Impurity could be the starting material of these solvents. What are the starting material of these solvents? Their protonated form. Their protonated form means chloroform. Let's say CdCl3. How we make that? We did the deuterium, we did the proton exchange with deuterium. So the impurity is chloroform. So a little impurity, let's chloroform or simple DMSO or acetone or methanol, is impurity in your deuterated solvent. Now those impurities will help you to get the reference peak in the NMR. Help you to get the reference peak in the NMR. As you can see a NMR profile of a compound in this slide, the sample is dissolved. I do not know what is this sample. I do not know what is this molecule, right? But this sample is dissolved in CdCl3 for NMR. We want to do the NMR of this sample. We dissolve the sample in CdCl3, but the CdCl3 have impurity, which is chloroform. So CHCl3 is an impurity. Now this CHCl3 will show up on 7.24 or 7.26 in your spectrum. See this peak at 7.24 or 7.26. So this is the reference peak. This is the reference peak. You can consider this is a reference peak. Why we need the reference peak? Because we want to have the reproducible results. We want to have the results of accurate frequency, of accurate value. So we always set the reference peak at 1 ppm. ppm is the value or is the frequency that we measure in. So the unit of frequency in NMR is ppm, as you can see here. So impurity is CHCl3, which we set up at 7.26 ppm. Once you set up the impurity CHCl3 hydrogen at 7.26 ppm, now you know rest of your spectrum will have the same 7.26 ppm at 7.26 ppm. So you can compare the spectrum with each other. You can compare the NMR spectrum with each other. That is the benefit of having the same value of NMR solvent in every spectrum. Right? Same value of NMR solvent in every spectrum. So that's the reason we need a reference peak, right? Let's move forward. All right. So basic things clear. Basic thing clear means what is the basic thing? That what is the instrument and how we make the sample. What kind of solvent we can use for the sample. Now we see about the NMR. How we interpret the NMR. Basically, we see the NMR. We see always the chemical shift. The most common term for the NMR people to use is chemical shift. Chemical shift means where your molecule hydrogen or carbon is showing up in the NMR. So you can calculate that frequency via this equation. Via this equation. Now, of course, we can always follow this equation to calculate the frequency, but we don't have to. We don't have to. I will explain to you later how to remember the values. That is quick and easy to know. So here is the nucleus. As you can see, here is the nucleus. Do you want to do the NMR of? Nucleus is rotating, of course, the circulating electrons, right? Circulating electrons, so they have their own magnetic field. They have their own magnetic field. Now you apply the magnetic field. This is the applied magnetic field. B naught. B naught is the applied magnetic field that we apply from the instrument. As we just see in the instrument that we have the magnetic coils that apply the magnetic field. So B naught is the applied magnetic field. Once you apply the magnetic field, the electrons have their own magnetic field, right? So they will counter each other. Either they will be in the same direction or they will be in the opposite direction. If they are in the opposite direction, they are countering each other. If they are in the same direction, great. I mean, they are enhancing the magnetic field. So what that means, this have very big impact in your NMR. How? We will discuss that. That once your nucleus is surrounded by more electrons or less electrons, what that means is once your nucleus is surrounded by more electrons means you have more magnetic field. You have more magnetic field which is generated from the electrons and countering the magnetic field of the instrument. Or you have less electrons means you have less magnetic field, so there is a less counter effect of the magnetic field of the instrument, right? This all we will discuss with the examples, not just by theory, but I will give you the example. Then I'll explain to you why and how it will work out. So on this slide, we just need to remember one thing. Why I'm showing this slide means why. What is the significance of this slide is to know that the nucleus have the electron revolving around the circulating electrons. They have their own magnetic field, and we apply magnetic field B naught, which is from the instrument. We should know these things, which is important to understand the next example. Now let's move to the example. As I said, I'll explain everything with the example. So let's see, very simple molecule is acrylonitrile. Hope everybody is listening me, right? Everybody is listening, right? Great. All right, let's see the example of acrylonitrile. Very, very simple molecule. Acrylonitrile have the double bond and the nitrile group. Nitrile is cyanide, CN, right? All right. So as I said initially that there are different frequency NMRs exist, but once we go more than 100 megahertz, we have to use advanced NMR. Advanced NMR means the Fourier transform NMR. See, 60 megahertz, you can see here, right? I given you all the spectrums. I given you all the spectrums of different frequencies of acrylonitrile. See, 60 megahertz, how the spectrum look like. 100 megahertz, how the spectrum look like. 300 megahertz, how the spectrum look like. You can see the difference, right? See, what is the basic difference is at 60 megahertz, all the peaks are coming in the cluster, all one together, one on each other, one on each other. Very hard to interpret, because they are not separate from each other. So it's very hard to interpret how this the peaks belong to which proton. 100 megahertz somewhat solve the issue, somewhat solve the issue. 300 megahertz pretty clean, pretty clean, pretty clean. See, all the peaks are separate. I will explain to you how these peaks show up now. So, all right, let's talk about the NMR. You can see I label the protons A, B, and X. Remember, we are talking about the protons. Two kind of NMR, proton NMR and carbon. Two kind of NMR, proton as well as carbon NMR. So the proton NMR is this. Proton NMR shows up from 0 to 14 megahertz. 0 to 14 hertz frequency, 14 ppm, sorry, 0 to 14 ppm. All the values, all the proton highs between 0 to 14. But in carbon NMR, it goes from 0 to 250 or something, 0 to 220. So the value, the frequency or the hertz is different in proton and the carbon NMR. Why it is different, that we'll explain later on. First, we have to see that how to interpret the NMR of acrylonitrile or any NMR. Sorry, any NMR. You have NMR and you can see a set of peaks. You can see the set of peaks here, right? You have some peaks here. What these peaks show us? What these peaks show us? You have some proton in the molecule. Of course, you have some proton in the molecule, right? So the molecule is acrylonitrile. A, B, X is the protons. So now how to calculate or how to interpret the NMR of the acrylonitrile? See, now we have to understand one thing. As I just mentioned in my last slide, we have to know more electron or the less electron? Huh? We have to know more electron or the less electron. More electron or less electron means electron negative group or electron positive group, electron withdrawing group or electron releasing group. So cyanide is electron withdrawing group. Cyanide is electron withdrawing group. Cyanide attracts the electron towards itself, means it reduces the density of electron on the neighboring carbons. Now, see, HA, HB, HX. I already label in this NMR is A, B, and X. So how to see NMR? All right, see one thing. Let's say we have this proton, this proton, this proton. This is all along the double bond, right? This is all along the double bond. So here is not only the simple proton, but here is also the cis and trans kind of stuff. Who understand? I think everybody understand that the molecule with the double bond and have the different group on the vicinal carbon can undergo the rotation and can show that the molecule is having the cis stereo configuration or the trans stereo configuration. Now HA and HX is trans to each other, is trans to each other. HB and HX is cis to each other. So how proton NMR shows up? Proton NMR works on the basis of the environment. Different environment means, see, HA and HB. HA is in the environment of HB. HA is in the environment of HX as well, but is very far from each other. HB is in the environment of HA, but HB is in the environment of HX here as compared to HA HX distance, isn't it? So thing is that HA will be, HA is in influence of HB, HA is in influence of HX. Remember one thing, the trans coupling is higher as compared to the cis coupling. What that means? Coupling means the trans protons will be wider, will be far away from each other as compared to cis. You can see here. See, okay, now how to know? As you can see in the spectrum, I have three different set of peaks, A, B, and X. A is having two set of peaks. You can see two set of peaks in A, right? Two set of peaks in B, right? You can see some peaks, four different peaks in X, right? All right. A have doublet of doublet. Now this called doublet of doublet. So there are singlet, doublet, triplet, quartet. We should remember these four kind of pronunciation or the way to say the peaks shape. Singlet is this. You can see in the X. You have singlet, 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 singlet. This easy to say singlet, but I will explain what is singlet or what is thing. So this is singlet. So this thing is in the A. You can see doublet. You can see two peaks in one peak, 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 right? It's called doublet. Now they are doublet of doublet. What that means? So how the peaks show up in NMR? How the peaks show up is, you have a proton, that is in coupled with another proton. So n plus 1. How many protons you have in the surrounding plus 1, that many peaks should show up in your NMR. Means HA must show two peaks. Must show two peaks because there is only one proton in its surrounding, which is Hb. Right? In principle, it should show only thing. It should show only one peak, two peaks, right? Only Ha and Hb. But the thing is that Ha is also in influence of Hx. That also will be splitting. So that's why you can see doublet of doublet. Now this small doublet is born from HAHB. The big doublet, as you can see, I mentioned here 20 hertz difference between these two peaks coming from the trans coupling. Coming from the trans coupling, right? Coming from the trans coupling. So trans coupling means they are far from each other. Now we talk about the B. B is having the cis coupling. Of course, B is in influence of A. So of course will be doublet, as I just said, n+1 means the proton have the one extra peak. How many protons is in the next carbon? As we discuss some more example, it will be more clear. So just to understand here, the thing is that cyanide is electron withdrawing group. It withdraws the electron. So once it withdraws the electron, all the carbon, all the hydrogen shifted towards downfield. Shifted towards downfield because they are in the influence of the external magnetic field. None of the electron or very few electrons is shielding them from the magnetic field. From the magnetic field. What that means? As I said, cyanide is electron withdrawing. It withdraws the electron from the neighbor carbon, means the electron density reduced on this carbon. If the electron density reduced on the carbon, means those carbon is more in the external magnetic field, means they are de-shielded, means they are downfield. So once we talk about that downfield and upfield, downfield of the NMR is, or down shielding of the NMR is to go on the left of the NMR, means the value will increase, means you will see more peaks in the down of NMR. Down of the NMR means towards higher number. Upfield means towards the lower number. Let's see another example. Now you see this example, huh? Methyl benzoate, right? You have one methyl group. In a neighbor of this methyl group, there is no proton. There is only CO bond, right? Is easy example to understand. Is easy example to understand. NMR, that methyl group having a no proton in its carbon vicinity. The carbon next to the methyl group is having no proton, only oxygen. So there is no coupling. No coupling means there is no proton to couple with this CH3. This is very far, CH2. CH2, this CH2 is very far. Proton NMR does not show the coupling of that far. See how many bonds? 1, 2, 3. No, no, no. So only up to 2 bonds. Only up to 1 or 2 bond maximum. Huh? So the thing is that this CH3 neighbor carbon does not have any hydrogen. So there is no coupling. So n+1. What is the value of n? 0. Because there is no proton. So n+1, 0 plus 1 is only 1. So it will be only singlet. Understand? There is no proton on the carbon next to the carbon or next to the methyl group. So there is no coupling. So n+1 means 0 plus 1. N is 0 here. There is the number of hydrogen next to the methyl group is 0. So n is 0. So n+1 means 0 plus 1. 0 plus 1 is equal to 1. 1 means is singlet. So this singlet near to 2 is belongs to the methyl group. Now we talk about the next peak. What is the next peak? Is CH2. There is no other hydrogen here, right? In between. only oxygen. So another hydrogen is here, CH2. Now this CH2 having no hydrogen next to it here. See, this hydrogen, this carbon having no hydrogen, there is oxygen. So there is no hydrogen next to it. Of course, again will be singlet. Again will be singlet. N plus 1, 0 plus 1, 0, singlet, right? So this CH2 will show up here. See this around 5.2. Now move forward. You can see very small peak is about 7.24. This belongs to CdCl3 impurity chloroform. As I mentioned in our first few slides, that the solvent we use to dissolve the compound to check NMR is CdCl3. That CdCl3 have a impurity which is chloroform. Chloroform is here, right? All right. So this is the chloroform. Okay. Now what is this? The next huge peak, the set of peaks. As I can, if I expand here, you can see the expansion. You have multiple peaks. This belongs to aromatic phenyl ring. So we have to understand one thing. I was telling you before in couple of slides before that I will explain to you how to interpret or how to see NMR quickly. That aliphatic, most of the aliphatic protons show up before 0 to 6 ppm. Most of the aliphatic protons show up from 0 to 6 ppm. Aromatic protons shows from 6 to 9 or 10 ppm. 6 to 9 ppm, because heterocyclic like pyridine, piperidine, pyrazole, those protons sometimes shows up at 9 ppm. So very high, huh? Very high. So protons of the aromatic region shows up around 6 to 9 ppm. Aliphatic region shows up from 0 to 6 ppm. Remember this. Remember this. All the aliphatic 0 to 6 ppm. All the aromatic 6 to 9 ppm. Huh? So here the aromatic is around 7.4. See how many protons? 1, 2, 3, 4, 5. You have 5 protons. All those protons have one next to another, right? What that means? This proton is in influence of this proton. This proton is in influence of this proton. This proton is influence of this proton. But this proton is influence of only this proton, not this proton, because there is no proton. What that means? All the protons are in influence with each other, and there is no other functional group present on the benzene ring. What that means? There is no other environment, no different environment for the proton. Means they all shows up approximately at the same place. Approximately at the same place, right? All right. So I wrote the title of the slide is effect of electronegativity. What that means? Effect of electronegativity. As I said, electronegativity. Electronegativity means to withdraw the electron. Now the people who understand that this is the ester group, right? Ester group is electron withdrawing group. It withdraws the electron. It withdraws the electron from the CH2. Generally, the benzyl CH2, benzyl means the CH2 attached directly to the benzene ring is called benzyl. That CH2 generally shows up around 4.5. Generally shows up around 4.5. So this hydrogen generally shows up around 4.5 in the NMR, but here we can see that these shows up at 5.2. Shows up at 5.2. Why? Just because of the ester group present next to the CH2. Because ester group withdraws the electron from the CH2, make it more deshielded, make it more deshielded. What that means? It's more under the magnetic field of the instrument, means is more downfield, is more aligned towards the magnetic field of the instrument. So remember one thing, if you have electron withdrawing, if you have electron withdrawing group, your peaks will shift towards the towards down means towards higher value, towards more bigger number. If you have electron releasing group, your peaks will shift towards lower number, right? Let's move to the another slide. As we will discuss more example, your concern or your curiosity for the NMR, the characterization for the NMR will be more clear. Huh? Let's see. Right. So far we have discussed the singlet, doublet, right? We have discussed singlet and doublet. We will discuss the triplet. We will discuss the quadret. But all those peaks, doublet, triplet, and quadret, the difference between these two peaks, let's give you the example. I was showing you the NMR of acrylonitrile. I told you the difference between two peaks, 20 hertz. What that means, 20 hertz. The coupling constant between these two peaks is 20 hertz. What that means is 20 hertz. What is the coupling constant? Coupling constant is the distance between the two peaks in the resonance of one nucleus. It tells us how one proton is under the influence of another proton, how one hydrogen is under the influence of another hydrogen. This is the significance of coupling constant. Coupling constant tell us how important it is that the neighbor of the proton is present in the molecule. I will tell you with example why it is important. The symbol of coupling constant is J and is not depend upon the magnetic field. It's not depend on the. Now, see this. Very easy to understand. Here I pin down peaks for you. This is triplet, 3 peaks. One small, big, small. Triplet. This is quadret. Small, too big, small. So singlet, you already seen. This is singlet. This is singlet. Doublet, you already seen. This is doublet. Or just say this is doublet. Now you saw triplet. This is triplet. One small, one big, one small. This is quadret. One small, two big, one small. So what is the coupling constant? Coupling constant is nothing but the distance between the two peaks. Distance between the two peaks. How to calculate the distance between the two peaks? I will explain to you how. So it tells us amount of interaction between the two set of hydrogen creating that multiplet. Multiplet means more than singlet, right? Doublet, triplet, quadret. So singlet, doublet, triplet, quadret. So that's called a coupling constant. Now, how to see that? How to see? I shown you the triplet looks like this, quadret looks like this, but in reality, how it is? Let's see the example of ethyl benzene. Ethyl benzene, CH3, CH2, phenyl ring. Now see this CH3, this CH2, and this is the phenyl ring. This CH3 is in the influence of this CH2. This CH2 is in the influence of this CH3 as well as in the influence of benzene ring, right? Now let's talk about this CH3 first. This CH3 is in the influence of CH2. What that means? These 3 protons is in the influence of these 2 protons. So n plus 1. These 3 protons in the influence of how many protons? 2 protons. These 2 protons means n is equals to 2. So 2 plus 1, 3. So triplet. So this 3 protons should show triplet. These 3 protons should show triplet because the neighboring it have 2 protons, right? So the triplet of this 3 protons is about at 1 point something. So this peak, as you can see, around 1 point something is the triplet. One big, one small, one big, one small. It's something like this. See this triplet. One small, big, and small. Now, so this CH3 is here. Let's see this CH2. CH2 is under the influence of CH3 and this carbon, but this carbon does not have proton. Only this carbon have protons. So how many protons? Three. Three. So what that means? N is equals to 3. So 3 plus 1, 4. So it will be quartet for these two hydrogens. It will be quartet for these two hydrogens. So CH2 will show quartet. This is a quartet. See this quartet. Quartet is this. See, small, big, big, small. Right? Small, big, big, small. Because n plus 1, n is equals to 3. This CH2 is under the influence of these 3 protons or these 3 hydrogens. These 3 hydrogens is n is equals to 3. So n plus 1, 3 plus 1, 4. So 4 means quartet. So that's why this protons, CH2 proton shows quartet, right? All right. And the benzene ring as same as before. As we said, they all are coupling with each other. There is no functional group, so all of them shows up almost in the same place, almost in the same place as about 7.45 or 7.3. So in this spectrum, once you see this spectrum without giving you the molecule, what you can see, you have some aliphatic group. Aliphatic means without aromatic, of course. Aliphatic means some CH3, some CH2, huh? And you can see some aromatic group. So without seeing the molecule, without seeing the structure of the molecule, you should be able to tell from the spectrum that what kind of molecules, what kind of NMR you are having, what kind of NMR you are having, kind of NMR you are having, right? So if I see that, I can tell you that we have a aliphatic region, you have a CH3, CH2, aromatic region, of course, you have aromatic rings, aromatic protons, right? Now, you should, after you see that, okay, we have aromatic ring, we have aliphatic protons, right? The next thing is to know what kind of proton is methyl, is methine, is ethylene. What kind of protons is that? Huh? So that you can see from the coupling, that you can see from the multiplet, is singlet, doublet, triplet, quartet. So the peak at 1.2 or 1.3, peak at 1.2 or 1.3 is triplet. What it give me the indication? It give me the indication that the carbon present next to this carbon having 2 protons. Now I will see the peak at 2.4 or 2.6 or whatever is that the quartet. What it shows Hello. I hope everybody can hear me now.
Now,
Right.
yes, you can go ahead.
All right. All right. Thank you. Thank you. Thank you. All right. so okay, I was telling the one thing that we should be able to see the difference in one thing, that the CH2 connected directly to the phenyl ring here shows up around 2 point where 2.45, 2.6 ish. I was considering this thing. See this, CH2 connected directly to the phenyl ring shows up at 5 point something. CH2 connected directly to the phenyl ring shows up at 2 point something. Now you know what is the difference between the electronegativity. Now we know what is the difference. Electronegativity consideration is important. Why electronegativity consideration is very important? Because here the CH2 was connected with the electron withdrawing group. There CH2 is connected with the electron releasing group. Methyl is electron releasing group. That's the reason it shifted the peak towards the upfield. Upfield means towards the lower number. Lower number means, you see, 2.6 or 2.7. There it was around 5 point something. It was downfield. I'm telling again and again downfield and upfield because these terms are very difficult, very important to remember. In NMR, people use upfield, downfield. Downfield means towards the lower side, towards the higher number. Upfield means towards the lower number. Okay, so electronegativity makes the difference, right? Let's move to the another slide now. So far we discussed the protons or the hydrogen present on the carbon. So far all the examples I shown you, all those hydrogens are present on the carbon. It does not mean that all the hydrogen present on any of the other atom will also behave in the same way as they behave with the on the carbon. No. Proton, the hydrogen present on the carbon and hydrogen present on the oxygen is two very different things. OH and CH. CH and OH. CH, that hydrogen is not in the influence of any other electrons, but OH, NH, SH, all those hydrogens are in the influence of other electrons, as well as the electronegativity difference between hydrogen and those atoms. Electronegativity difference between carbon and hydrogen is also there, but not as much as of oxygen, nitrogen, and sulfur. So protons on oxygen, nitrogen, and sulfur are exchangeable just because of their high electronegativity nature, just because of their partial ionic nature, just because of their partial ionic nature. Just because of their partial ionic nature. So partial ionic nature means you can see on this slide that proton on oxygen, nitrogen, and sulfur are exchangeable. They are subject to hydrogen bonding. They are subject to hydrogen bonding. What that means? Hydrogen bonding means, you see, OH undergoes hydrogen of the OH undergoes hydrogen bonding with another oxygen. Is intramolecular hydrogen bonding. Can be intermolecular as well, depending upon the solvent you use for the NMR, right? Now we will have a break now here. Yeah, we will have a break now here on this slide, and I will leave this slide, leave the session for now, and we'll start in 15 minutes. But you guys must think about that, why and how we can avoid the hydrogen bonding of the ethanol. Let's say this is the NMR of ethanol. This is the NMR of ethanol. You can see ethanol, CH3, CH2, OH, right? This is the NMR of ethanol in CdCl3. What happens if this ethanol I dissolve in any other solvent? CdCl3 is a non-polar solvent. What happens if I dissolve this in DMSO? Is a polar solvent, isn't it? Is a polar solvent. What happens? What will happen if I dissolve the ethanol in the DMSO and then take the NMR? Why they are exchangeable? As I mentioned, they are of ionic nature. So we will discuss after this, after 15 minutes, on this topic of protons on oxygen, nitrogen, and sulfur. So we will have now break for 15 minutes. Now the time is 6:20. We will be back here at 6:35. If anybody have any questions or concern, they can ask now, or else we will be back by 6:35.
Dr. Mohit, Varun Agarwal has a questions. Uh,
Yes, sir.
how we choose base peak in NMR spectra?
Okay. Okay. Uh, I cannot see the question. I cannot see the question. I don't know why. Anyway,
Varun, Varun, I have
Varun.
unmute you. You can ask.
Okay, sir. Hello. Good
Yes,
evening,
yes,
sir.
yes, yes. Hello, hello,
Uh,
hello. Good evening, जी. हाँ जी.
uh,
बताइए.
sir, I want to ask that how we choose the base peak in NMR spectra, as we use TMS as reference peak.
Okay, so the thing is that, see, TMS, once you use TMS as a reference peak, it really depends what kind of solvent you are having for your NMR, right? Not all the solvent have the TMS. Only few of the solvent have TMS. But the thing is that how you choose a base peak is, as I said in my first slide or first few slides, that every solvent have the impurity. Impurity is their protonated form, is their hydrogen form. Hydrogen form is CHCl3. So the base peak in those NMRs is the CHCl3, which shows up at 7.24 or 7.26. But of course, is great if you have TMS standard. If you already have TMS in your solvent that you use to dissolve your compound, great, you have the TMS. That peak will shows up at 0, right? TMS always shows up at 0. So that peak, of course, you can use as a base, as a standard. But remember, you will not use that solvent having the TMS. You will not use TMS solvent if your compound is having silicon, because TMS is nothing but trimethyl silicon, right? So TMS will not, you will not have the silicon, you will not have the compound, you will not have the solvent as the TMS if you have compound with the silicon. If you have the compound with the silicon, so you will not use that one. So
Okay, sir.
basically, most of the time people use the CHCl3 or the protonated impurity or the, okay.
Okay, sir. Thank you, sir.
Yes, 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 definitely, it's okay. All right, I think it's the time to start back our conversation on NMR. So, as I said before our break, that we will be discussing on the protons on oxygen, nitrogen, and sulfur. They are exchangeable. Why they are exchangeable? Why the carbon, hydrogen, protons are carbon, hydrogen is not exchangeable? Why that hydrogen is not exchangeable? It's just the reason is pretty simple. We are able to understand the electronegativity difference. We are able to understand the partial ionic character of the molecules. If we are able to understand partial ionic characters of the molecules, we are able to judge that what kind of hydrogens are exchangeables in NMR, right? The thing is that now these hydrogens undergo hydrogen bonding either with self or with the solvent you use for the NMR. Now, for the NMR, the thing is that is depend upon the application to application. Is depend upon the application to application. You so sometimes we have to use the protonated, so we have to use the polar solvent because most of like sometimes the compounds are not soluble in any of the solvents, so we have to use DMSO. DMSO is like a saving hand, DMSO dissolve almost all of the compounds. If your compound is not soluble in any of the NMR solvents, you can use DMSO. It will dissolve everything. No? So if you use DMSO, of course, the oxygen present in dimethyl sulfoxide, those oxygen undergo hydrogen bonding, have hydrogen bonding with the alcohol, moiety. So what is the effect? What is the effect? Let's say, see this, right? Now there is hydrogen bonding with the solvent. Uh, the partner to do the hydrogen bonding. So here structure of CH2OH. CH2 you have CH3. Means somewhere some now that OH, let's see about CH3 first. CH3 is connected with Chitkara. We have two hydrogens now. These two hydrogens, so and is equals to so 2 plus 1 3 means CH3 of the triplet is 1.0. The big triplet, all base uh, CH2 is in influence of CH3, of course, n plus 1. So, sorry, n plus 1 means what? It shows the thing. To 4, small, very small. The now comes with 4. Now, what means now exchangeable?
Dr. Mohit,
Why?
sorry to disturb you. Your voice is breaking a little bit.
Okay. Now is okay.
Yeah, it's okay. You need to repeat earlier versions so that it can be clear more.
Okay. All right. The thing is that what I was saying is that we understand one thing here, that CH2 is in influence of CH3, is in influence of OH, but CH2 is showing the quartet or pentet because CH2 is in influence of CH3 and OH. So 3 hydrogen here, 1 hydrogen here. Total 4 hydrogen, 4 plus 1, 5. So pentet. but it's showing only quartet. Why? Why? The flipping, because the flipping. Now, these are subjected to hydrogen bonding. Hydrogen and oxygen is subjected to hydrogen bonding. What that means? They are tied up. They are not in the rotation, or they are not having the exchange. How to say that? The thing is that the hydrogen present on the flipping, flipping, because they are in the hydrogen bonding. So oxidation is low. The relaxation low. What that means? That means not in the influence of. They are not participating in the coupling. They are not participating in the coupling. That's the reason you see the peak singlet. The peak coming from the OH is singlet, because the oxygen of the oxygen is not participating in any coupling. Is not having any coupling because they are in the hydrogen bonding. Let's see the example of DMSO molecule. CH3 CH2OH, CH3 CH2 ethanol in DMSO. In DMSO. Now, DMSO, now the hydrogen is not in the hydrogen bonding, in the intramolecular hydrogen bonding. You see, it was in intramolecular hydrogen bonding, self hydrogen bonded. DMSO no, because DMSO is polar molecule, polar solvent. Polar solvent it involves the hydrogen present in ethanol in hydrogen bonding with DMSO. What that means, the intramolecular hydrogen bonding is absent. Is absent. What that means? Now the hydrogen is available. Now the hydrogen is available for the coupling. Now the hydrogen is available for the coupling. So what will happen in the P and NMR? Let's see. First CH3, CH3 will show triplet because two protons, two hydrogen in the neighbor. You can see triplet. CH2 show quartet. Oh yeah, will not show quartet, will show more than that, because CH2 is in the influence of CH3, which is in the influence of OH. So total 4 protons, 4 plus 1, 5. So total 5 hydrogens. So 5 hydrogen means pentet. Pentet is here. See 1, 2, 3, 4, 5. So 3.49 is the pentet. Pentet. Some other splittings are also coming. It's just because of the exchangeable protons. It's just because of the how the oxygen hydrogen behave in the magnetic field. And oxygen hydrogen is in the influence of CH2, means n plus 1, 2 plus 1, 3. So oxygen hydrogen should show triplet. All right, you can see the triplet at 4 point something, 4.3. DMSO is at 2.49. DMSO is at 2.49. Very small peak, very small peak, 2.49. So I hope I'm able to clarify the concern on oxygen, that if we have the protons on oxygen is not as same as on the carbon, is not as same as on the carbon, right? All right. Let's go forward. Now we discussed already the proton on the oxygen. Let's see about the nitrogen. Now the nitrogen containing molecule, the nitrogen containing molecule, the nitrogen having 14 and nucleus have the spin of 1, right? So proton attached to it, and then there is no NMR of that. There, so the thing is that complicates the picture, because the rate of exchange of proton on the nitrogen and the quarter per moment of the nitrogen. Thing is that protons on the nitrogen undergo rapid, intermediate, slow exchange. I am talking about the isotope of the nitrogen, which is active for the NMR. I'm not talking about the 14 and 7. All right. talking about the isotope of the nitrogen, which is active for the NMR. So if the proton is present on if the hydrogen is present on the nitrogen, undergoes rapid, intermediate, and slow exchange. Different kind. If it is rapid exchange, you will have the signal. Slow exchange, no signal. If the exchange is rapid, the NH proton is decoupled from the nitrogen atom, and hence the proton will be adjacent to the carbon atom. The NH proton peak is therefore be the sharp singlet, of course, right? Now we'll see. I'll explain all these things. Whatever is written in the text, I'll explain in the with the spectrum. So we have to understand one thing, that when the hydrogen is present on the nitrogen, they can undergo rapid, medium, and slow exchange. Different kind of protons, different kind of hydrogens, right? As you know, amine salts, so those called amine, NH, right? And they can be distinguished by having the primary, secondary, and tertiary amines, right? All right. Let's see the example. As I said, I'll explain with you with the example. Let's see the example of ethyl and methyl carbamate. Huh? Ethyl and methyl carbamate, right? Carbamate is NHCO2. Huh? NCO2 is the carbamate. Gonna be. All right. So the point here is where are the peaks? If we see this spectrum, again, I will say one thing. Once you see the spectrum, we should be able to grasp which showing what kind of peaks are here. You have triplet, you have doublet, you have quadret. You have one broad small peak, huh? You have one broad small peak. You have three sets of proton, CH3, CH2, CH3. So three big peaks. You have NH, you have NH proton. Now what is what? Huh? See one thing. This NMR is in CDCl3. This NMR is in CDCl3. Thing is that this NH hydrogen is under the hydrogen bonding with the oxygen of the molecule itself. They are under the hydrogen bonding. It's very, very hard to understand the proton spectrum, the hydrogen spectrum of nitrogen. Very hard. They always jump, they always dance from one place to another place. They always dance from one place to another place. It really matters the concentration. It really depends upon how you shim your sample. As I said initially in the starting, right? You have to shim your sample. It's really important how you shim your sample. What is the concentration? What is the molecule? So many factors. Oxygen molecules, oxygen hydrogen is way simpler to interpret as compared to nitrogen hydrogen. Let's see here. Now you will have, so see, CH3, CH2 means you will have one triplet, one quadret. Where is the triplet? Triplet is at 1.2. So this CH3 is coming at 1.2 with the triplet. You have one quadret, of course, you have one quadret at 4 point something. Agree? You have one doublet. What is doublet coming from? See, this CH3 is under the influence of NH. This CH3 is under the influence of NH. NH is having only one hydrogen, N plus 1, 2, doublet. It should show doublet. It should show doublet. So this is the doublet of the CH3 present next to the nitrogen. Now nitrogen is under the influence of 3 hydrogen on the carbon. But are they splitting? Hard to say. It's just showing me the broad peak. It might be quadret if I increase the frequency of my NMR spectrum, NMR machine. I do not know, right? It's very, very difficult to tell what kind of splitting nitrogen hydrogens are giving us. Very hard, very difficult. Very difficult. So this is another example of, so this is an example of the nitrogen having the NMR of the molecule having nitrogen. Another C will see the fluorine. Not only hydrogen, not only hydrogen, coupled with hydrogen, hydrogen coupled with fluorine as well, hydrogen coupled with fluorine as well, because of the integer value that we discussed initially on the first slide. For the table I said, so 19F isotope of the fluorine shows NMR, fluorine NMR, and it participates in the coupling as well. So as you can see, and remember, fluorine shows very strong coupling. It shows wide range coupling. It shows the long range coupling. Long range coupling means, you will see here what that meaning of the, what that means, the long range coupling. Long range coupling means, see, CH3CO CH2F. This CH3 is having the coupling with this fluorine. This CH2 as well is having the coupling with this fluorine. So CH3, CH2. Now CH3 is coupled with fluorine, N plus 1. How many fluorine? 1 fluorine, N plus 1, 1 plus 1. 1 plus 1, 2. So it should show doublet. Now this CH2 is in the influence of fluorine. This CH3 is in the influence of fluorine. Right? Long range, small range. So both of them shows the doublet. Both of them shows the doublet because both of them in the influence of fluorine. Both of them are in the influence of fluorine. CH2 is at 4 point something. CH3 is at 2 point something. Why? Both of them are in the influence of fluorine. So both of them shows doublet because there is only one fluorine. And remember, fluorine shows small as well as long range coupling, short and long range coupling. Fluorine spectrum is not easy to interpret. It always gives the messy results. If somebody have the experience to deal with the fluorine spectrum and have the big molecule with the fluorine attached to the aromatic ring, oh gee, this is very hard to identify each and every proton because it coupled with every proton. Let's see another example. Another example, let's see about the 1,2 orthodichlorobenzene. Orthodichlorobenzene. So why this example, or this example also is important, is that this sample, this molecule have a plane of symmetry. This molecule have a plane of symmetry, right? You can see plane of symmetry. If I divide or if I cut the molecule into half, they're equal, right? Yeah. What that means, the set of peaks, you see, the set of peaks. If you see the same set of peaks, you see the same set of peaks, they have the same, right? This, all are same set of peaks, right? If I, so the molecule with the C2 symmetry, the symmetrical molecule, if I cut it, it have the plane mirror symmetry, means it shows the same set of peaks. It shows the same set of peaks. So how to interpret the aromatic spectrum, that will discuss with the time. But I shown here example that spin coupling equivalence means, if you have the symmetry means your molecule can be divided into half and have the same structure, so it can shows the couple, the mirror image of the peaks. Now another example, another typical example have the high ketone. The the people who understand the chemistry behind the keto-enol form, they will appreciate this example by saying that how the molecule exists in the keto and enol form. Molecule exists in the keto and enol form means, see, 15% of the ketone form, diketone, 85% of the enol form. Because the reason is very simple, is electronegativity. See this carbonyl molecule having electronegative character, then attract the hydrogen as, oh, we can say that they are in the present in the enol form and have the hydrogen. That hydrogen is under the electronegative hydrogen bonding is more stable. Why? Now let's see this example. See, this molecule shows you this. You can see methyl groups. Where's the CH2 of the ketone here? You see another methyl. You see another methyl. See them. So it's a mix of NMR, right? It's a mix of NMR. It doesn't make any sense. You have, if you have this NMR all belong to one. Doesn't make any sense to me, because you see this is long, methyl again is here very near to each other, but both are in the same environment. Why they split into two? There's no meaning to have that kind of thing, right? What that means, the molecule itself in the solution form exists in two different forms, keto and enol form, and both NMR showing here. Enol form is in the major. You can see the CH3 from the enol, you can see CH from the enol, right? This CH from the enol. You can see OH from the enol, but from the ketone is very less. You can see CH3 from the ketone, you can see CH2 from the ketone, but the amount you see, you can see the NMR concentration. You can see the NMR concentration, right? So thing is that you have the mixture of both keto as well as the enol form. You have the mixture of both keto as well as the enol form in a same solution. Right? All right. So the purpose to show here this thing is because some of the molecules undergo rapid interconversion in the solution form, as you can see in this one. As you can see in this one, that they undergo rapid interconversion between the one form to another form, right? Between one isomer to another. So keto as is happening here in this molecule, as that can be shown in the NMR as well. Now, okay, this we'll talk later on. This is the same thing that we talk about the magnetic equivalence or the coupling equivalence. On this slide, that we have the mirror image of the peak, right? All right, let's move forward. Now the rotation around the double bond. So, all right, styrene. I'm taking all the different example because it's very important. It's very important to understand all the different cases. It's very important to understand all the different cases we face through our daily life in the lab. Once you see the example of styrene, as you can see here, you can see the example of the styrene. The thing is that I have the set of protons, right? I have the set of protons X, A, M. Some is at peak is at 5.2, some is at 5.7, some is at 6.7, some are showing the 7.2. So from this, first of all, Identify the molecule that you have some aliphatic, you have some aromatic, right? Easy. Aliphatic means below 6 or 7 is aliphatic. Above 7 is aromatic. So above 7, you can see some aromatic peaks. You can see some aliphatic peaks. Now the aliphatic peaks, remember one thing. Above 5, if there are some aliphatic peaks, that mostly belongs to the double bond kind of stuff. Double bond or triple bond kind of stuff, right? So the thing is that here the styrene molecule hydrogen present at the terminal carbon can undergo rotation. Can undergo rotation means HX, as I explained before, HX can undergo coupling with HA as well as HM. HX can undergo coupling with HA. So what will be the coupling? Doublet, because HX is in influence of HA as well as HX is in influence of HM. So doublet from here, it will be doublet of doublet. You can see here 4 peaks, right? 1, 2, 3, 4. Actually, this is not quadrat because the intensity of all the peaks are almost same. Intensity of all the peaks are almost same. They are not quadrat. They are doublet of doublet. They are doublet of doublet. Okay. HA and HM. Why? They are in the influence of HX. They are in the influence of each other. They are as well doublet of doublet. They are also doublet of doublet. How? They are influence of each other, so they are showing doublet. They are influence of HX. They are showing that coupling as well. Now the protons from the aromatic region. Protons from the aromatic region. C, A prime, B prime, C. You have 3 kind of protons. A prime, B prime, and C. A prime. Environment of A prime hydrogens are different. B prime hydrogens are in the influence of A prime, and C proton is, or C hydrogen is influence of B prime. So C will show somewhere triplet or 3 peaks. B prime will multiplet. A prime is somewhat doublet or somewhat triplet. I mean, it will be the mixture because it's hard to identify, hard to say what kind of. So generally, mostly aromatic proton shows up multiplets. Aromatic proton shows multiplet. Huh? All right. So I was able to explain to you that why the protons around the double bond is important to understand because they rotate. They rotate means they show the different kind of coupling. Why? Now, another example we take here, as I said, as we'll move towards the slides, I will give you more example of each and everything to understand much better concept. Here is another example of electronegativity. Nitro group. Nitro group also is electron withdrawing group just because the oxygen, the structure of the partial ionic character present in nitrogen, in the nitro group. That's the reason they are electron withdrawing. Now, because of that electron withdrawing, we see here CH3, CH2, NO2. By seeing the NMR, you don't have to see the structure. By seeing the NMR, you must be able to interpret what kind of NMR, what kind of structure it exists. So, what kind of structure it exists? I have triplet. I have 2 triplets actually. I have 2 triplets. I have 1, 2, 3, 4, 5, 6 septet, 6 hextet. Huh? I have hextet. I have 2 triplets. I have hextet. All right. 2 triplets coming from where? 2 triplets is only means I have 2 CH2s. I have 2 CH2s. Those 2 CH2s giving the triplet in my NMR spectrum. I have somewhere between 5 or 6 protons. I have five hydrogens that giving me hextet. So let's see. You have at one something, one triplet means at one something you have the 3 hydrogens showing you the triplet. 3 hydrogens showing you the triplet means they are under the influence of CH2. So CH3, CH2, easy, huh? Now that CH2 also is in influence of another CH2? Could be, because I am having here one hextet. That hextet is coming from 5 plus 1 rule, right? 5 hydrogen plus 1, so 6. So how the 5 will come? On one side you have CH3, on other side you have CH2. So you see CH3, CH2, CH2, and right? CH3, CH2, CH2. This CH2 is next to the nitro, because nitro group is electron withdrawing group, is highly electronegative, withdraws the electron from the CH2 and become deshielded. So that's why you have very high magnet. You have a downfield, huh? You have downfield, right? All right. So that's the reason. Here is the stuff about the electronegativity. Let's move forward. Now the chemical shift equivalence. Chemical shift equivalence means what kind of hydrogens are equivalent? What kind of hydrogens are equivalent? How we say that they have some symmetry or not symmetry? As I just explained to you, that some kind of hydrogens, some kind of molecules are symmetrical or not symmetrical, Hana? So so we really have to see what kind of symmetrical element present in our molecule. Axis of symmetry, plane of symmetry, center of inversion. I'm not going to give details on those because that will be out of my topic for today, but just for the brief, that we have different kind of topic relationships in our environment, in chiral environment, right? Is a homotopic, is enantiotopic, is diastereotopic, right? Homotopic, they can be interchanged by axis of symmetry. Enantiotopic, everybody know what is enantiomer, right? Enantiomers, the protons in a mirror image environment. Diastereotopic, no symmetry elements, right? No symmetry elements. So just to keep in mind what kind of protons are what kind in what kind of achiral environment. Achiral environment means what kind of achiral environment means? The environment before pre to the chiral center. That could be chiral center as well, right? So homotopic, anisotopic, diastereotopic. So for example, just a very simple example, dichloromethane. Dichloromethane, DCM, is a very common solvent in the organic lab. It have the C2 symmetry because it can divide, have the plane of symmetry as well, right? So the protons are homotopic and the chemical shift are equivalent. Because means what that means, the both hydrogen will have the chemical equivalence. They are under the same environment. Chlorofluoromethane, now they are enantiotopic because they are under the different environment. They are the mirror image of each other, right? Sorry. So all right, now the thing is that those are also enantiotopic in example 3, the cyclobutane, right? Right. So no much details. I'm not going to. I will share the slides with you. You go in the detail with the slides. But my concern here is to show you that okay, this is another example of the anisotropic group. You can see that these have the plane of symmetry, sigma symmetry, right? And also here, but these examples, the hydrogens present on the top, they are not anisotropic, but yes, they are anisotropic with respect to the lower ones. All right. So how to deal with those kind of NMRs? That's the main concern. how to deal with those kind of NMRs. That once you have the NMR of the diastereotopic protons and how it works. So these protons are diastereotopic. Huh? These protons are diastereotopic. Let's see the NMR first. You have a doublet of doublet. You have a doublet of doublet. You have an OH. You have some aromatic protons. You have some aliphatic. Aliphatic, you can see the singlet, means there is no environment, no hydrogen present next to one of the group. Now, what is the group? These protons are 3, so methyl group. Methyl group does not have any hydrogen present next carbon to it, so that's why it's showing singlet. Okay, so you see this methyl group is this one, right? Of course, the OH is here. Now the HA and HB, these two are diastereotopic protons. These two are diastereotopic protons. So that's the reason they appear at different, because they are under the different environment. They are under the different influence. They are under the different influence. You can see that one up and down, right? Up and down means they are either the influence of the methyl or the hydroxy, any of the environment, right? Because the next carbon, penultimate carbon next to it is having the methyl and hydroxy group. So the A chiral center is there. Chiral center is there. The chiral next to that is having the diastereotopic protons, because one of the proton, if you replace, will be chiral. Right? This is the A chiral center. So anyway, the thing is that the diastereotopic protons will show up at a different value because they are in the different NMR field, right? Let's see about the dimethyl adipate. Dimethyl adipate. See this molecule having the plane of symmetry. Is a symmetry, right? You divide the molecule into half, it will be two. Same thing. So this molecule will not show two different methyl groups, it will show one methyl group. Not show you A prime differently. No, it will show you the same. It will not have base prime separately. No, it will show you the same. What that means that when the symmetrical pattern shows for the peaks over with each other, right? Now, this will already explain how around the double bond, how the bond work out. To have the double, you have the A center, how those peaks around some double bond.
Sorry, Dr. Mohit, your voice is again broken. Dr. Mohit, your voice is broken.
Hello, hello.
Yeah,
So
go
you can
ahead,
hear me
please.
now,
Go ahead.
right?
Yeah.
Yes. Yeah. All right, all right. So the thing is that here we can see that the rotation around the double bond concept is the same. We should able to switch which peaks belongs to where. All the aliphatic peaks, here is no aromatic. Compound spectrum is in CDCl3. You can see the CDCl3 peak at 7.2. Now you have the double bond, you have that single bond. The double bond, of course, will show, right? all the single bond below that. Now, what kind of thing say? A big peak at one point something. The huge long peak is these. They are in the influence of one CH. Both are in the influence of CH. Means only one hydrogen. One hydrogen means N+1 means 2, right? 2 means doublet. It should show doublet, right? It should show, but it might not. Why? Why it might not? You see this? Oh, this hydroxy group present here, right? Because of the rotations around the electron, sometime the hydrogen behave. It does not mean that we are not. It does not mean we cannot identify the spectrum. In those cases, we have to take another spectrum, C13 or something, or depth or nausea something, right? So, so what will happen? You have the hydrogen here, you have the hydroxy group here, right? Hydroxy group present in the methyl group. Now, the close vicinity of the methyl group, that's the reason maybe the splitting will be different. So, as we move forward, as we go to the complicated structure, we need the help of the detailed NMRs. We need the help of the we use C13. C13 NMR, the NMR is different than the proton NMR. As I said initially, the isotope of carbon is in very less abundance. So we have to we should spend longer times. On this, and the intensity or the range of the peaks are in the long range also, right? So as you can see here, just an example I'm giving you for the C13 spectrum. Don't see the upper one, see the down one. This is the C13 spectrum of this molecule, of this molecule. So you can see that here the range is very high. It's not from 0 to 14. I mean, it goes from hundreds, right? It goes in the hundreds, and you can see that what carbon belongs where. So we will not go in the detail of this because the time does not allow us. The thing is that this will be the another session. We will have another session on the proton, on the carbon 13, on the C13 NMR and their applications, along with the application of the proton 1H NMR. We will have another session on it. So if somebody is interested, then we will that somebody all of those can join in our the next session for the C13 NMR. So I hope I was able to make you understand somewhat some concepts about proton NMR. Now I will be taking the questions. If anybody have any concern or questions, please go ahead.
Okay. Dr. Mohit, there are some questions from the
Okay,
audience. Uh,
sure.
Number one, if the molecule is symmetrical, then why one set of peak is downfield and other is upfield from Dr. Wajid Jafri?
So the thing is that as we are seeing that one set of peak is downfield or one set of peak is upfield is just because of the electronegativity is the molecule present. The thing is that the set of the molecule, let me go back to the slide.
Okay. Next is It is also from Dr. Wajid. Please let me know about the C13 NMR session.
I will, sir. I will definitely post, and we will let you know. Yes, definitely. Where is the slide?
Okay, next is from Varun Agarwal.
So you
Sir,
see
can you
the
explain?
so as we see that if the molecule is symmetrical, the upset or downset of the downfield or the upfield of the peaks is just because of the electronegative group present on that, or the different functional group present on that. It's of course we have to see that the hydrogen next to the functional group, hydrogen next to the chlorine in this case here, of course they will show the up and down. Of course, the hydrogen presently, if I divide this into half, not all the hydrogen is next to the chlorine. Some of them have the long range coupling, some of them have the short range coupling. So the long range and the short range coupling, of course, the hydrogen present next to the electronegative atom will be more downfield. That's the reason you have the two set of peaks, the downfield and the upfield. All right. So what is the question from Harun?
There is one question from Varun is, sir, can you explain quadrupole moment?
Hello. Yes.
Yeah,
So
one
the thing
one
is
question
that
is quadrupole
yes,
moment.
yes,
Yeah.
yes. The thing is that what is the quadrupole? Quadrupole movement generally shows up in the nitrogen because see, nitrogen molecule, nitrogen atom, hydrogen is as I said, the rapid exchange between those, and they all themselves have their own magnetic behavior. They have their own electromagnetic field. So once you place them in an external magnetic field, of course, the magnetic field generated and the magnetic field of the nitrogen itself, because nitrogen have the lone pair of the set of lone pair that generates the quadrupole movement. Quadrupole movement is nothing but the slow exchange or fast exchange of the hydrogen between the magnetic fields, as how your nucleus is exchanging your proton in between the magnetic field. That's how the quadrupole moment is a term used to define the exchange of the hydrogen between the different magnetic fields, between the different atoms. All right.
Okay, one more question, sir, from Varun. Sir, how do we decide radio frequency pulse in megahertz?
Radio frequency pulse in megahertz.
Yeah.
So radio frequency pulse in megahertz, I think I don't know what the question means, radio frequency pulse in megahertz, but I would like to say that the NMRs generally we do is 300 megahertz or 400 megahertz. If you are talking about the coupling constant that need to be calculated, yes, that can be calculated by taking the difference between the peak intensities multiply by the frequency of the NMR spectrophotometer. That may be 300 or 400. And what else you want to know, you can tell me. I think I did. I don't know what you mean by the radio frequency in megahertz. Can you be more clear or more elaborate the question?
One more question also from Varun also. If in a compound there are more than one symmetry elements, present, then how we will study the spectra?
Yeah. So the thing is that's why I said once your molecule gets complicated, once you have more set of peaks, let me show you one example. See this sample. I'm not saying that this have the symmetrical molecule, but the thing is that once the NMR, once the proton spectrum get complicated, we need the help of the depth. We need the help of the depth. We need the help of the NOSI. We need the help of the COSI. We need the help of the HSQC. We need the help of the HMBC to study all those parameters and align all the proton and the carbon along with the NMR. So only the proton NMR will not help in those cases. Of course, it will help up to certain, but still the problem will remain same. You will not be able to identify which hydrogen. So if you want to make sure for that, we have to study the depth. We have to study the HSQC. We have to study the NOSI. We have to study the NOE. So that I will all. So in the next session, I will cover the C13, NOE, and NOSI. So you will be who are having the better um, clear picture about those things.
Okay, Dr. Mohit, one more question. Due to voice problem, Dr. Warjit can't hear about the dimethyl adipate explanation.
Let me go back there.
Okay.
All right, I am on the slide of the dimethyl adipate. The thing is that I just want to say here that we do have the symmetry here. We do have the symmetry here. So because of the symmetry, you can see the set of peaks. All the peaks are in the thing is that you will see the set of peaks, but you will not see at the different place both the methyl, both the CH2s next to the next to the ester group, and the penultimate and the one more CH2 present in the center. All those is shown at the one set of peaks. So the thing is that what I want to say is that all those set of peaks will be because of the symmetrical molecule. Now, how you can say that or how you will say that, that will be covered in the next session.
Okay, thank you, Dr. Mohit, and thank you,
All right.
audience. Okay. Any questions, sir? Any questions from audience?
No, no, no. I
Okay.
don't have. I mean, if they have something they can ask.
Okay. One more question is here also. One more question, sir.
Yes, yes, yes.
W- Regarding radio frequency pulse. No. It's okay, sir. It's okay.
All right, all right. Thank you, everyone,
Okay.
and hopefully we will be seeing you. We will be see you in the next session as well, and we will have more details and a more clear picture about C13, NOSI, and HSQC. Thank you, everyone.
Thank you, Dr. Mohit. Thank you, audience. Varun, you are unmute. You can ask directly to Dr. Mohit.
Yes, sir. Sir, I wanted to ask that, we say that our NMR instrument is of 1100 megahertz or 900 megahertz or something like that. So how it is decided? That what I was asking.
Varun, I think Dr. Mohit is in offline now. So
No issue, sir.
you can write the questions. To write the
Oh,
questions. I will pass these questions and we'll give the explanation on this.
okay, sir. No issues. No issues. Thank you, sir. Thank
Is it okay for you?
you. Yes, sir. Fine, sir. Fine.
Because you are already enrolled with Dr. Mohit for a couple of days, so you can
Yeah,
clear this
yes.
NMR.
Yes, sir.
Okay.
Yes, sir. Yes, sir. Sure, sir. Sure.
Thank you. Thank you very much.
Thank you, sir.
Okay.
Thank
Bye
you.
bye. Take care. Okay.